Okay, so we're going to talk about Michael addition. There's two different kinds, or two different ways it can add, either 1,2 or 1,4. We're going to talk about both. The first one is 1,2, and at the top here it just goes over how the mechanism works with either a strong nuke or a weak nuke. A strong would attack first and then protonate, and then a weak nuke would protonate first and then attack. So the first one we're going to talk about is 1,2 addition. That involves strong nucleophiles, including Grignard reaction or an R group attached to lithium. So how the 1,2 addition works is that it will attack here, so the Grignard or the other strong nucleophile will attack here at the carbonyl carbon, and then it'll form these resonance structures where the bonds and lone pairs can flip, allowing that negative charge to be moved throughout the compound. And then there's the steps for that. 1,2 addition is also under kinetic control, which means it will occur faster. And this little note about a strong base will pull off an acidic hydrogen and then attack that refers to the weak nuke, which we will talk about right now with 1,4 addition. So with 1,4 addition, that is under thermodynamic control, which will convert to the lowest energy product, which will be the keto product as opposed to the enol. Keto has the lowest energy because it is more stable than the enol. The enol has a negative charge. Tautomerize is, the definition of that is basically flipping between the keto and the enol form. So we're going to go through a mechanism really quick, and then the steps are also listed down here. So the first step up here, the strong base will pull off the acidic hydrogen from the nucleophile, and those electrons will flip back onto that carbon. And then with step 2, the nucleophile attacks the beta carbon of the electrophile right here. And then those electrons do almost a double flip. They flip onto that carbon, the alpha carbon, and then they flip to make that double bond in between the carbonyl carbon and the alpha carbon. This, in fact, causes the double bond between the carbonyl carbon and the oxygen to flip up onto the oxygen as a lone pair. From there, that oxygen is going to steal a hydrogen from a water molecule, just in solution, and then this will create the enol product. From there, the OH, that base, is actually going to steal that hydrogen back, flipping the lone pair back onto the oxygen, and then which in turn flips back down to form a double bond between the carbonyl carbon and the oxygen, and then which pushes those electrons of this double bond onto the alpha carbon. And then the alpha carbon with the negative charge will pull off a hydrogen from a water molecule, and then this in turn forms our keto product. So we go from the enol over here all the way to the keto as the final product. Here's a little note about the keto product has lower energy, which in turn increases stability, and the exact opposite for the enol. The last section of chemactivity 37 that we're going to talk about is the Robinson annihilation, which is basically the formation of a ring through Michael addition and aldol condensation. So the mechanism is right here. The base pulls off the acidic hydrogen, and the electrons from that bond fall back onto that carbon. The nuke then attacks the electrophile, going through that double flip of the electrons, and then in turn flipping the electrons of the carbonyl carbon and the oxygen back onto the oxygen. So then we have our nucleophile and electrophile attached at this point. The oxygen gets protonated, and then it goes through the whole Michael addition, where it becomes deprotonated, and we come down here to this section where we go through the tautomerization between enol and keto. Then we're going to come over here to the aldol condensation. So this is the area where it actually forms the ring. So from here, the base took off a hydrogen from the alpha carbon on the other side of this oxygen carbonyl carbon. And then from there it formed that negative charge, which in turn will attack the carbonyl carbon of this aspect of the molecule. Then from here we have our two-membered ring formed with the extra lone pair from this double bond flipping up onto the oxygen. It will get protonated, and then we're going to come down here. The base will then steal a hydrogen from in between this double bond O and the alcohol. Those electrons are going to flip back onto the carbon, which in turn will flip back to make a double bond between these two carbons. The alcohol the electrons from that bond will flip back onto the OH group, creating that strong base that we started with, giving us our final product. So an example really quick of the 1,4 addition. This OCH3 is coming in, stealing that hydrogen. It's going to flip back on to the nuke, which in turn will attack this electrophile, bumping up those electrons from that double bond. This will in turn grab a hydrogen from that base that stole the hydrogen at the beginning, and then going through the steps, this will be our final product.